So I will not talking about Calavials today, but surfaces nevertheless. And let me just a couple of comments. Geometriewerkstatt.com, that's my homepage where you can find much of these pictures, videos, and also 3D print data if you are just interested too, and which means in German, Geometry Lab. So we start with some applications. So I was told that we should start very basic, and and I would like to tell you what you can do with surface theory. Okay, because I'm normally interested only in two-dimensional objects in 3 dimensions, which is really restrictive, but that's the world we're living in after all, right? So this picture here, on the right, left, my right, shows actually a human brain, okay? All these beautiful structures there, and apparently surface theory is used to map out how your brain looks like, and it's really important to have it in a in a conformal way, meaning that you have angle preserving data, which will show you where exactly the places that you'll do mathematics in your brain, for example. Okay? Since now I'm living in Beijing, oh no, this one is minimal surfaces, which is a fake picture because as you can see, there's air inside. That's definitely not minimal, but it was the most suited picture I could find of such a soap film inside, with black background. I have pictures with other backgrounds, doesn't fit so much into this picture here. But you can also find minimal surfaces in nature, basically in butterfly wings. Okay, if you zoom in, you can see these triply periodic minimal surfaces in there. This thing is called gyroid. And very funnily, it was first discovered by a physicist, Alan, and then discovered in nature, not the other way around. Okay, so we can find a lot of surfaces in nature and also in architecture. I was living on the other side of the street of this building here, and what integral transforms does basically for architecture is you start out with a curve, you want to transform it in some way so that in between these lines you have planar squares you can fit your glass in, right? You don't really want it to be curved too much, but then still have a nice structure. And this side is from computer graphics. Okay, you would, in your favorite video game, you would want to deform some structures there because, well, you don't want to render everything again, but maybe you want to still read what is written on there, so you want the angle to be preserved, okay? And in this way, you can deform a cup into a torus, and still, it's everywhere. You can, fit your texture you had in the beginning, fit on there, angle preservingly, okay? And if you were here in Ross' talk yesterday, he was talking about the space of potentials, and how they did this flow is really exactly by just L2 deform linearly to 0 and somehow project on the way to the submanifold of surfaces. Okay, it's a very numerically works really well, and you need some type of technology to actually do it. It's if you do it intuitively, like just moving your triangles, it will develop singularities really fast numerically. So now this is a blood cell, and it is a Wilmot surface, so meaning critical surface of the bending energy, and you have the enclosed volume divided by the surface area, somehow constrained. Okay, so that's how it looks like, and so you can describe what is going on in your body. Basically using surface theory. There's a little propaganda video maybe about what kind of mathematics I'm doing. And one motivation for me doing that is because you can do pictures, that's why. Okay. And it's fun to talk about after all. Okay, so for me, in all this setup, what is most interesting to me would be if I have a Riemann surface, meaning a surface, two-dimensional manifold, with a way to measure angle on it or a complex structure on it, I would like to put it into space optimally. Okay? So on the left-hand side, I have my domain, and I identify the top and bottom, left and right, to get a torus. And this one is the Clifford torus. Ross talked about this before yesterday, and it's just a stereographic projection to R3, and you can see the curvature lines here. They intersect orthogonally, and these correspond to the coordinate lines here, so they are angle preserving. Well, the map is angle preserving. And Ross talked about energy, Wilmer energy. So it's basically how much the surface is bent. And in biology, it's called Helfrich energy. And there's something, it has something to do with the Loeffner energy in stochastic processes. So this Schramm-Loeffner evolution stuff. Basically, somehow these energies, and I don't understand that too much, but it's kind of the renormalized area of something. And that's basically the Wilmer energy if you do it in hyperbolic space. So it has some connection to that. And it measures somehow the roundness of your surface if you interpret it geometrically instead of the bending. And whenever you deform something conformally, meaning angle preserving in your ambient space, then the Wilmer energy will not change. Yeah. And all these minimal surfaces, also constant mean curvature surfaces, meaning you blow a bit air into a minimal surface. So this cube picture I showed you, those are all examples of constrained Wilmer of these surfaces. Yeah, so we want to optimize such kind of geometric PDEs, okay? And the goal in my study is to find examples, like the Clifford torus, which is kind of a simple one, investigate the properties, but also just investigate the properties of the moduli space of all these solutions that are compact. So let's start with tori first. Sphere is kind of trivial. We have learned that it's a kind of a round sphere, and then there's, for some multiples of 4 pi energy, there's basically one or a moduli space of Wilmer spheres with that energy. But it's not something that is constructed using integrable systems or anything. So it's not necessarily well, it's understood. Let me put it this way. So let's start with tori. And for tori, if you really want to fix the Riemann surface structure, then we have somehow this typical picture. That should be a half. I hope that's correct. And the conformal type of the Clifford torus is really the square being given by these 2 red vectors there. Okay? And if I change to another Wilmer torus, this is a equivariant Wilmer torus. The equivariance type is 6, 1. That's why you have 6 lobes. And the profile curve you rotate this with is kind of ellipse, or looks like an ellipse. So this one has some other conformal structure. I'm not claiming that this is this one, okay? Now, the conformal structure has somehow a symmetry when you just reflect it with respect to your imaginary axis, and basically that corresponds to turning the surface inside out. Now, if we have the space of immersions, I can map the thing to the conformal types, the space of conformal types. And the question, most of the time, that map is locally a submersion, except for at isothermic surfaces. And we are interested in the question, what are the Wilmer minimizers if I fix that point here? Okay. So this is a theorem Ross claimed stated yesterday as well. Whenever I have an example in that particular conformal class with energy below 8 pi, then I know the Wilmer minimizer exists and is embedded. Okay? Well, we can nowadays use Ross results as well, just saying exist. Okay? And moreover, the Wilmer Euler-Lagrange equation looks like follows. This one is just the Wilmer equation. So it's a 4th order nonlinear PDE. And here we have 2 Lagrange multipliers, lambda and mu. And these 2 are just the 2 directions in the plane, okay, for the torus. And at isothermic, these 2 are not linearly independent, which causes all sorts of problems. And in particular, all these minimal and constant mean curvature surfaces, which are far easier than the actual Wilmer surfaces, because it would have only h equals constant, so there's only 2nd order, they are of this type where the two constraints are linearly dependent, which causes kind of problems. So examples of those are rotation of a closed curve just in upper half plane, and you rotate around the x-axis, and you can interpret the upper half plane as a hyperbolic plane. Then it would be an elastic curve in this hyperbolic plane, and the rotated surface would be constrained Wilmore and isothermic. So it must be constant in curve-shaped space form by some theorem of Richter. And they always have rectangular conformal type because the two directions, the curve direction and the rotational direction, is perpendicular to each other, and they are closed. So let me start. Yeah. So this is a family of surfaces that goes along these imaginary line. It's constant mean curvature in S3. And as you can see, when the conformal type goes to infinity, we end up into planes, okay, two geodesic spheres in S3. Yeah? And can go back. And the two-law conjecture says that those surfaces, which are CMC in S3, would be minimizing the Wilmore energy in these rectangular conformal classes. Okay? So what is known? Well, there's a result by India and Schätzle saying that very close to the Clifford torus, and they call it Clifford tori, we would rather call it homogeneous tori. They are constrained Wilmore minimizers, unique ones, close to the square cluster. So at the very beginning of the video I showed you, they are actually minimizing. And then we have shown, this is me and Sebastian Heller, that's why H squared, and Sheikh Ndiaye, we have computed that this whole family is actually constrained Wilmore stable. Okay? Not only among immersions that would affect fixed conformal class, but for all A when you go to the left. And the problem here is basically when you identify all these things is when you have isothermic, it should be locally CMC in a space form. But then if you, for example, have elastic figure 8, that's definitely not CMC in S3, but actually CMC in H3. And the H3 looks like for this blue shaded area. So the surface actually intersects H3 perpendicularly, goes out of H3, come back again, and the outside is also an H3. So you have two minimal surfaces, CMC surfaces in this case, outside and inside, which are not congruent at all, but they glue together smoothly to that CMC surface. Okay? So the minimal example, the first one was first discovered by Babbage and Bobenko. And for the minimal ones, we have a whole line of umbilicus. And so when you classify these things here, okay, like those isothermic constraint Wilmore immersions, even with constraints, energy constraints and so on, you would need to think about this complete different class of integral equations because the other ones are Sinch-Gordon and these are Cauchy-Gordon equations. Okay, so just that these somehow in a very different connected component of your moduli space. And since right now, basically, the only stable constrained Wilmore immersions are these two lobes, the figure 8s are actually considered, conjectured at least, to be constrained Wilmore stable in this other connected component. Okay? And when the mean curvature goes to 0, this drop here becomes small, and it converges to the so-called asymptotic solution of elastic curves. And if you put this point here to infinity using a conformal transformation, then we get a catenoid. Just saying. So the minimal, so it's not closed, and the minimal one is not contained in the class. So the minimizer here should not exist, in a sense, in this connected component. So we did some experiments on how these constrained Wilmore minimizers should look like. Let me just start the video. So we started at some conformal type and some examples, and you can see these are the candidates for the minimizers using the flow of the computer graphics paper I told you before. Okay, so that's how they would look like. The question is, how do you identify these immersions, right? I have even more pictures. So we have very close to the Clifford torus, it has this little spin in here, and if you go to the right-hand side in the conformal type, it would look like more twist. And this is a two-lobe, and you have more twist. It's a kind of very consistent picture. Okay? And we can numerically just compute the energy, and there's some, of course, bugs and so on. But what you can see is, first of all, at the origin, so meaning at the imaginary axis, we have that the slope here is non-zero, and meaning that the minimizers here should be isothermic. And we can classify the isothermic surfaces below 8 pi in some other work. And moreover, we have some evidence that this slope should be concave. I mean, these things here should be concave. Yeah? So I'm pulling out these things I've with Ulf Wagner 12 years ago, because I do think that right now we might have better tools to actually show some of this picture. Okay. But what else is known, so something I showed with Czech and Dai, is when you go starting from the Clifford torus a little bit to the right, then we can identify these pictures, so you can actually find the parametrization of these surfaces, and they are so-called 1-2 equivariant. So basically, they depend only on the curve. So these are when A is very close to 0, so very close to your rectangular ones, and you go to the right from the Clifford torus. That's what we can show. And what are the main difficulties? Well, I told you the isothermic ones are singularities of the moduli space. There are multiple sheets of of proper surfaces intersecting these isothermic surfaces, definitely at the Clifford torus. And you have to find the right branch, basically, to go off from there and find the ones that has really least energy, and at least even find a way to singularize the space. So that was the main difficulty here. And even find an idea of how that could be, what is true in this picture, basically. So that's something. So now that I've told you about minimizers, I would like to say, well, the space of these isothermic surfaces are really, or CMC surfaces now in R3 maybe, are also really pretty, okay? So this is the content of the soul curve conjecture, which says start at some cylinder, then you can bend it basically always, into a closed CMC surface in R3, okay? Basically, it's closed at every rational time, and that is how the conformal type goes. And here you would have, that's a lobe count, right? This is the conformal type, and this was the spectral curve of that integrable system, if it tells you something, okay? If not, let me just show you this thing again. You start with some cylinder, and then you see these red points coming out, the singularizes a space you have, and bend the cylinder into a closed surface. So the conjecture is that is true for all CMC tori in a sense, that you can split the space up into half dimensions of curve, half dimension of cylinder. And then you can just bend it into the shape you want. Okay, and that's how you can try to understand the moduli space. And then, if you are interested in how these closed solutions would behave under integrable transformation, isomonodromic transformations, you see that these cylinders in certain directions which correspond to the curve would behave just like the curves, as you expect, I guess. So that's how this look like. Well, it's very conjectural, but I do think that nowadays we have more tools, again, to work on these type of questions, and even to make it rigorous what it means, right? So these are just experiments. Now, what about higher genus? I talked half of my talk now on tori, and I would like to say something, at least, what happens with higher genus. Compact surfaces now in S3. I'm sorry, I'm jumping through these space forms because they all have somehow different behavior, but they're somehow also related. But whenever you really want something compact, you have to, the different space form behaves differently. Okay? So for higher genus, there's not that much known. These are so-called Lawson surfaces. They were discovered by Lawson in 1970. Okay? And so you see the sphere. You see the Clifford torus. This is a genus 2 surface. And these patches are symmetries of the surface in S3. So this is 3-1. Theoretically, it would look like this as well, but it's a different stereographic projection to show that they have a hyperelliptic symmetry. This is 2-2, which has genus 4, which is basically this one, but with a layer added to it. That's why it has suddenly genus 4. And you can go on. So basically, for every K and every L, you can find such a thing, and the genus K times L. Okay? Yeah. So you have the symmetry, and let me show you how this is constructed. So what you do for the G1 surfaces is you would project, or this picture is at least made to project your S3 to R3, stereographic projection, so that this is a geodesic in S3, and this is a geodesic in S3, which doesn't intersect. Now, the geodesic 2 sphere in S3 is mapped to S2. Okay? We divide this piece here in 2G plus 2 pieces, and we take 2 neighboring points. And we take this one into 4 pieces and take 2 neighboring points. This gives me a polygon or foregon, which I dip into soap and have a solution of my plateau problem. And with that piece, I can build the surface, okay, like so. So basically what it does, it's to rotate once, okay, rotate another time around this other geodesic, it's different stereographic projection, and rotate around the z-axis. And now this is a different stereographic projection, and then we just make a symmetric form by changing the point. Okay, so now this is a genus 2 surface. Okay, and you can see because of these angles here. Okay, so this is a right angle. You can only do this one rotation. You cannot do it multiple times, otherwise it will overlap. But now this is double that angle. And now how many turns you can make, right, to get as many handles as you want is how big that angle is. Okay, that's why the angle basically is 1 pi over G plus 1. Okay, and maybe I just stop this video here first. Stop. So this is known results. And even if these G1 surfaces are expected to be the Wilmot minimizers of genus G, but only very recently, actually, so these are Wilmot conjectures and Lawson conjectures. Ross was talking about also yesterday. And I should have said here, it's missing one information, that this G1 surfaces, now the index as minimal surfaces computed, that they are non-degenerate. So actually, we know now that you can deform these minimal surfaces a little bit into direction of CMC surfaces, and that moduli space should be one-dimensional because of the non-degeneracy. That's a quite recent result from 2020, maybe, by Capuleas and Weigel. So now, what is actually the main result I want to talk about today is first, we can use a different method, integrable systems method, to reconstruct these Lawson surfaces and show that they exist without using plateau solutions. And moreover, the large genus limit of this thing is just 2 spheres. Okay, well, that's what's known before. But what we can do now is we can compute, for example, because we have these parameterization quite explicitly, we can compute the area. Okay, and the Taylor expansion looks like follows. So we take the deformation parameter being our angle, right? And how this looks like is basically if you would start at the Clifford torus, you would cut it open at the curvature lines and bend it. And throughout all these bending, it remains minimal. And then at this place, where the angles are just right, you can add the piece in to get your genus 2 surface. Okay? So, and then we can compute the coefficient. The first one is just log 2. The second one being zeta 3, the Riemann zeta function. I should say before we could actually prove it, we put it into Mathematica, this like 15-digit thing, and that suggested us that this is zeta 3. And then we started out proving it. And the 8, alpha 5, alpha 7, it gets quite complicated, okay? But, so these are so-called alternating zeta values that appears, and well, it's just a generalization of Riemann zeta function. But you can see structure, because if you sum up all these things and use that log 2 is just zeta 1, then in each term, the sum is just 7 in this case, which is just the coefficient of your, the number of the coefficient, the index of the coefficient. So we have some now more understanding of, at least in the minimal case, how these coefficients look like, in which space they are. And I think, yeah, exactly. We can show that these coefficients has zeta values where your entry is only in 1 bar, 2, and 2 bar, and they sum up to the index of your coefficient. Right? So it actually suggests some more structure out there. And then we do that and show that the convergence radius is such that it corresponds to G greater equal 2.64. So the argument's using some implicit function theorem, and then you have something close to G equals infinity, right? Very large genus. And the idea is that you can call down to G equals 3. Okay, everything until G equals 3 is kind of covered by this formula here. And there's the bracket as well. Okay. It's very important that it's 2.64, by the way, because we have that, we can show that the Wilmot energies or the areas of these minimal surfaces are actually monotonically increasing in G for all G, because we have covered everything up to 3. The idea to show that convergence radius is by taking T now not as a real parameter but as a complex parameter, solving some holomorphic functions. Okay, so then you can have this error estimates using some type of Cauchy estimate. So basically, how just using complex analysis. And so then the first one is the Clifford torus, and there's a Wilmot conjecture solved for which we know the energy should be the minimizer among all genus G surfaces. So the only thing left was the genus 2 surface. We have very good error estimate on our G equals 3, everything above G equals 3, we can compute it is monotonically increasing. So we have only to work out some very rough, actually, triangulation of the genus 2 surface to show that this is below the genus 3. So that's why this 2.64 was really important to get a sharp enough estimate for the area of genus 3. So I think before it was 2.7 something, and that didn't work. Something like that. Or we would need to have some finer thing of that. So, oh, by the way, it is good that this is monotonically increasing, because if any type of min-max approach, which was the approach solving the Wilmot conjecture, would work here, you would expect those to be monotonically increasing. Okay. In the other direction, that's just a conjecture that whenever the Lawson surfaces KL, okay, have K prime and L prime bigger, but both bigger than K and L, that should be monotonically increasing as well. We can prove that for KL very large, and for finite ones, I think we have numerically computed everything till K equals 12, or KL equals 12. So basically, it is quite safe to say that this might be true. Yeah? So the other direction, as I mentioned before, is when you start at a genus G surface and just do the CMC deformation. Because this is non-degenerate, this is the unique deformation of your minimal surface into CMC surfaces very close to this one. And as you can see from the form, it's very similar to the two-lobe Delaunay surface tori I showed you before. It's basically the analogon of that. So this is conjectured, of course, then to be the minimizer in conformal class for higher genus. But I should say I can show, this is experimental because this we can show only for G very large. We didn't do the implicit function theorem thing because that was huge effort actually to do it for minima already. Okay, but we expect that to exist, of course. So let me, in a couple of minutes, tell you how to make these ideas of bending, opening, whatever, precise, not necessarily using analysis, but using gauge theory. Okay? So we start with the Riemann surface of genus G, and my map goes to either S3, considered as a Lie group SU2. Well, you can do the H3 as well and get some explicit non-abelian Hodge correspondence. That's why I have it here. Yes. And then on my SU2 cross C2 bundle, I basically have three different connections. The left invariant one, the right invariant one, which comes with the Lie group, and the Levi-Civita connection coming from my immersion. Okay? And the punchline is that the gauge between L and R is my immersion. Okay? So now I can reformulate the harmonicity of F, and also Willmore is kind of harmonicity equation for its mean curvature sphere in terms of flatness of connections. And the minus sign corresponds to S3, and the plus sign corresponds to H3 here. And this phi here is basically is the 1,0 part of F inverse dF. So the phi is basically differential. Okay? Now, we can relax this a little bit. So if you write it this way, then nabla L is basically lambda equals 1 and lambda R minus 1, or other way around. But we can relax everything a little bit by going through the Lawson correspondence that these lambda 1, lambda 2 needs only to be in S1. And what we need for this to work is this family here solving two different equations. Well, the one is that you have a first order pole with a holomorphic residue. That's somehow something that we can automatically get by choosing right ansatz. But the second is that it's unitary along the unit circle. And the third is that it needs to be trivial at 2 points. So we need a very good control on the monodromy problem of my family of flat connection. And when you have high genus surfaces, this becomes quite complicated because the fundamental group is non-abelian. Okay. So we have these conditions to solve. And well, the claim is, first of all, solving the PDE is far harder than finding that, which might not be true, whatever, but that's a philosophy. And second, the gauge class of the thing will basically determine the immersion already. So we don't really need that form. We only need the gauge map into the space of representations. Okay? So now, when you have that, it's really hard to come up with an example, right? Because you have all these conditions that to be solved. So when you start at something like a Lawson surface, what you do is reduce the complexity using symmetries. So what symmetry do we use? It turns out the rotational symmetry around the handle is the right one to do, because that cuts out for you a handle, and then you glue these together, and the angle here, which I call rho, is basically your pi over G minus G plus 1. So it's actually the genus of your surface, right? So if you glue this together, it becomes a 4-punctured sphere where if you go around this point here, you go around this angle here on your handle, meaning you have local monodromy, which is really the genus. The eigenvalues of local monodromy. And these points, due to other symmetries of the surface, we want to have the symmetry it's symmetric with respect to the real and symmetric with respect to the imaginary axis. So now, when we start at my nabla lambda here, which is equivariant with respective rotation because phi was df, okay? It has this symmetry. Then we can gauge it in a way that this one on the 4-punctured sphere would actually just become invariant and define something on the 4-punctured sphere. And here we know Riemann-Hilbert problem, rank 2. It's a Fuchsian system. Again, local monodromies of that Fuchsian system depend on the genus only. So for any genus up there, I have the same domain, and the parameter we use in the flow is the monodromy or the local or the eigenvalues of the monodromy of my Fuchsian system. And they're all the same at each 4 point. So we have now some setup which is reasonably simple, whatever, to use. Now, again, we want to use implicit function theorem to find these candidates. And the ansatz is, well, at t equals 0, or g goes to infinity, right, the local monodromies are 0. So that's how I reduced everything. So when everything is 0, then the good choice of your initial data is actually that you take the trivial connection. Nothing happens. And then the linear term is t times something, a Fuchsian system, right, which looks like this. So this here depends only on lambda, and it's SL2C, my Fuchsian system. But the eigenvalues of this thing, because in total it should be plus minus t, is plus minus 1. Now, because the connection family, this one here, satisfies this condition about unitarity and so on and so forth, right? These AIs now satisfy this equation in first order. Now, this is minus 1 because, again, eigenvalues was t and minus t. I factored that out. We only need one of these matrices because the 4 points were basically equal. And this is the linearized version of the unitarity condition. Again, plus refers to H3, minus refers to S3. And then we need that the monodrome is diagonal at these 2 zone points because when we go up, we want that everything to commute so that it becomes identity upstairs. Yeah? So these are the conditions we need to impose on DAI. Okay? AI satisfied. I mean, we find first AI that satisfy all this, and then we want to deform. Now, because this A1 depends on lambda, because my family depended on lambda, nabla lambda dependent on lambda, right? These 3 entries there will be holomorphic in lambda and an analysis around S1 with real coefficients because of unitarity. Yeah, because of the third condition. So these are our parameters, and basically we change these 3 infinite dimensional parameters to solve for eta lambda for higher order t's. And it turns out it works. Okay? So if you now need, it works, it gives you surfaces, it will have all these closing conditions upstairs if you like. There's not much more you can say if you don't want to. You can just ignore everything. But there's, of course, geometric interpretation, how to come up with the right initial condition. So the right initial condition is when you singularize the Lawson surfaces using the Shirk surface, which is a minimal surface in R3. By the way, if you have these 2 wings only, then there's a conjecture, a Shirk uniqueness conjecture, saying that the only minimal surface with these type of 2 planes at infinity should be the Shirk or the catenoid, which is actually part of the Shirk family. Okay. And since the phi again is df, you can, which is the lambda inverse part, okay, of my potential. So these are the coefficients of the potential. You can just write from the via stress data of Shirk the lambda inverse part of x1, x2, x3. And because you can do that, unitarity and all the other conditions will determine the other part. So it's at lambda equals 0, there's just no choice to be made. Okay? And of course, That's the minimal case where the planes are intersecting orthogonally. There's no reason why you cannot change the angle of the planes. That's how we get the CMC surfaces. And when the angle goes to 0, we have a catenoid after blow up. Okay, that's basically the main ideas, I guess, that went into the work. I guess my time is up. Done. Thank you so much.
So I know for CMC tori that in S3 that there's a one-dimensional family of deformations, but you said the same is true in higher genus?
Yeah, so basically this result by Kursner, Mateo, and Pollack is saying whenever you have some non-degenerate minimal surface, then the deformation space is one-dimensional. So just compact, has nothing to, yeah. And if you have ends, you have some other count. But
I'm really curious about your symmetric embedded surfaces. So I do algebraic geometry more than this. So the Riemann surfaces, for me, they want to have equations in space or something. So maybe one thing to start as a question. Thank you. The pictures are beautiful. Like, you've completely transformed the way that I visualize spaces of tori. It's absolutely amazing. So a surface of genus 2, I guess you would say.
Yeah.
And it has this additional, there's a hyperelliptic involution, but then I think you put maybe sometimes an extra.
Yes. Let me try. Is there a chalk somehow?
Like maybe like, oh, I need it out of the way.
No, I mean, it's a chalk. Okay. Oh, yeah. So I can write down the equation for you. And so it's, so if it's a, and then you have,
Yeah, I figured it was going to be a cyclic cover. But
yeah, well, I think it's 4 and 2, I mean, 2 and 3. And this would be 1, 2, 3, 4. And we assume that everything to lie on the unit circle. And basically, if that is P, then this is minus P bar, minus P, and P bar. So these are the 4 points. So it would be 1, 2, 3, 4 in this order. And this is the equation of your Riemann surface in genus G. So you have a lot of cover.
Is there any reason why these, like, you just can get your hand on them because they have these additional symmetries, but one could imagine other surfaces.
Oh yeah,
yes,
sure. I mean, it's just the simplest possible case we can get, because if you want non-abelian monodromy, the 4 punctured sphere is probably something you cannot really get simpler than that. I mean, without.
For other reasons.
Yeah, so basically, if you end up with 3 punctures and nothing is to be done, right? And there's nothing. Yeah, so you cannot do anything. But if you want to do something non-trivial but still, still accessible, it's 4. And then there are other constructions using 5 or 6, whatever. Yeah, you can do all sorts of things with that. But it's basically just right now the simplest possible case we can do. And that is still leading to these high genus surfaces, right?
So
do you have examples without symmetries?
Without, no. I mean, I think, well, it's not quite true. So you, what you can do is using analysis methods to glue, for example, 2 geodesic spheres with lots of handles. And that, I think, you can do kind of without symmetries. But if you do that, their implicit function theorem, it would be very much with very, very small handles, and you don't have that much of control. So when I'm talking about these Taylor expansions of our immersion, for example, of the potential, what we really have is that at every differentiation procedure, we have a polynomial of degree n+1. So we really get hold of the complete differential inside the Banach space. And if you do it using whatever inside W22, then normally the differential is also some W22 function and not something you can compute every coefficient of.
conformal structures. And in some points you have Wilmore minimizers.
Yeah.
You gave a condition, but then are there also points known where you don't have any? Or?
I think the idea is everywhere you have, because now you have, above the problem is rather whether they are immersed or not.
Mm-hmm.
So it exists, by Ross's example, result yesterday. But the question is really, is it a nice example, just covering of something, right? That would be maybe not geometrically just not nice to have. And the immersion thing is whether they have self-intersections or not. I personally won't like that either. But yeah, so I think that one is not settled. I mean, our experiments suggest, at least in that homotopy class, right? Because we started with a certain homotopy class that were preserved by doing deformation, that you do get self-intersections in certain. Thank you so much.
Thank you.